In part 13, we'll look closer at acid strength and structures, and what explains why some acids are strong, while others are weak.
Alright, so let's spend a little time here talking about acid strength and structure. Now, I almost always forget to include a question about acid strength and structure. I expect to have one online this semester. But essentially, if you want a good acid, right, a good acid donates a hydrogen. And so what we really need is a very, very weak HX bond, where X is just some generic acid formula, right? We want that hydrogen to just kind of fall off if you even look at it sideways. The weaker that bond is, the more H plus leaves. The more H plus leaves, the stronger your acid becomes. So there's essentially two things here that make that bond break easier. The first thing is if you make your atom larger and larger and larger, it gets a lot harder to hold on to that hydrogen. So if we're looking at HF, well, that's a very small bond. Those two atoms are about the same size, so F actually does a pretty good job of holding on to that hydrogen. Then you go to HCl, well, Cl is a much bigger atom, has a much harder time holding on to that hydrogen because they have to share orbitals, and it just doesn't share very well. HBr is even bigger, it's going to have even a harder time holding on to that hydrogen, and iodide is basically the biggest. It basically can barely hold on to that hydrogen at all. The second reason comes down to electronegativity. If that atom is pulling for electrons, right, it's trying as hard as it possibly can to grab those electrons, it's much more easily for that bond to just kind of suck into the more electronegative atom, and the hydrogen ion just kind of floats away. Now, under that logic, HF should be the strongest acid on the periodic table. And it's not. It's only a weak acid. So why is that? Well, one of the problems they have is the size of these orbitals are similar, so as a result, they hold on to each other really well. The second problem is that when F minus forms, it's a tiny, tiny, tiny little negative charge. Now, not tiny in charge, tiny in size. So the smaller a charge is in size, not in size of charge, but the smaller that atom is when it forms an ion, the stronger that charge is. And so some people say that HF is actually dissociated, but they stick together so strongly because those positive and negative charges are so near each other that it might as well still have a bond. But for the rest of the periodic table, as you go right, as your atom gets more and more electronegative, it gets much easier to steal those electrons, to put them on to that top atom, and let the hydrogen float away.
So most acids we will see in general chemistry are oxyacids. These are acids where the acidic hydrogen is attached to an oxygen, which is one of the most electronegative elements of the periodic table. As that oxygen pulls for electrons, which it always does, right? The atom that has the least electronegativity, the least amount of pull for those electrons is hydrogen. And so that is going to be the easiest place for oxygen to pull electrons closer to itself. As a result, that hydrogen atom is much easier to be broken. Now, as we put more and more oxygens on the outside of any molecule, right, what's going to happen is that those oxygens are not only pulling for electrons from the hydrogen, they're also pulling for electrons off the center atom of this molecule. So you can see the more oxygens we have, the greater that positive charge on that atom becomes. That atom does not want that positive charge, and so it needs to also pull for electrons. And so as all of these atoms are pulling for electrons, it becomes easier to break the OH bond to get those electrons, and so the acid becomes stronger. And that's why nitric acid and sulfuric acid are both strong acids, and sulfurous acid and nitrous acid are weak acids.
So we can look at an example of electronegativity here as you go from Cl to Br to I as we get less and less electronegative around that other atom. We see there's less and less of a pull from that atom to the oxygen, and then the pull from the oxygen to the hydrogen. So as the electronegativity goes down, the acid gets a lot weaker.
So we can talk about why some acids are polyprotic and others are not. It really takes a OH bond, and more importantly, it takes an OH bond with a strong oxidation state on that atom connecting to the OH. So we can look at citric acid, an organic chemistry acid, and we can say it is polyprotic. In fact, it's triprotic. It has 3 acidic hydrogens. And in fact, in organic chemistry, having an OH is not good enough. Right? What we really need is a COOH. This is known as a carboxylic acid chain, right? So we can see it has 3 acidic hydrogens because it's got one there, one here, and one here. But this OH over here actually doesn't have a strong enough oxidation state in the carbon to allow us to pull that hydrogen off. So we'll see that in other organic chemistry acids. So I'm not a big fan of these kinds of questions. We're usually not looking at 2 acids without more information. Right? We usually have a Ka or a Kb value or a pH we can measure. There's lots of ways we can figure out how strong these acids are. Nonetheless, if we just pick 2 acids off a shelf, HiO2 or HiO3, we would naturally say, oh, HiO3 has more oxygens, therefore this is more likely to be a stronger acid, and you'd be correct. And if we were to look at something like HbRO3 versus HiO3, similar kind of structure, what we'd have to do is look at the electronegativity values here. And that's something we haven't seen since Gen Chem 1. But if we look at these electronegativity values, we can see Br is a little bit higher. As a result, Br is going to pull harder for electrons. As a result, HbRO3 is going to be more likely to break off the hydrogen, and therefore HbRO3 is more likely to be a stronger acid.